Welcome to Hot Chips 32. Session 6, Networking and Distributed Systems.
Hello again. Sorry, a little bit of technical delay in getting this session started, and you might notice I'm not Yuan Xie. We will hope to have him online as session chair momentarily. For our first talk at this session, we have a presentation about Tofino 2 from Barefoot Networks, which was recently acquired by Intel. We have two speakers. Changhoon Kim is CTO of Applications and Barefoot Switches in Intel and an Intel Fellow. And Anurag Agrawal is a senior principal engineer and lead architect of the Tofino programmable silicon at the Barefoot switching division in Intel. So please take it away, and please comment on the Slack channel. Thanks very much.
Hello everyone, this is Anurag Agrawal. I hope I am finding you all in good health. I am here with my friend and colleague Changhoon Kim. We both work at the Barefoot Network division of Intel Corporation under Data Center Group. Together, we are very excited to talk about our next generation of programmable Ethernet switch silicon. Let's first understand, why do we need a programmable switch? These days, entire data centers are turning into this large warehouse scale computers with distributed compute and storage nodes. These servers needs to deal with the dynamic workloads, microsecond level service guarantees, reliability, scalability, high availability, just to name a few things. And if I can quote Amin here, the future computing platforms critically require more efficient, more reliable, and more flexible networks. Data plane programmability will be a critical ingredient in this quest. Clearly, the boundaries between compute, network, and storage will continue to blur and will require new system level architectures and easy to program systems. Switches, being the fundamental part of the network, are critical to enable rapid innovation and experimentation, to support large scale disaggregation, non-blocking bandwidth and zero queuing, in-network processing, end-to-end visibility through data telemetry, and many more things. Network operators and architects can no longer wait for 2 to 3 years of switching silicon development cycle to improve their operational flexibility. However, to design such a switch, we are butting against the conventional wisdom, whereby programmable switches are 10 to 100x slower than fixed function switches. They cost more and consumes more power. What customers cares about is the line rate, number of ports, latency, lower power. In order to design a switch programmable and meet these criteria, we needed a fresh thinking. So we studied few switching silicons and observed that the forwarding pipeline, which is predominantly responsible for the packet processing, consumes nearly 30% of the silicon area. And power dissipation roughly followed the similar distribution. So if you observe that the IOs take large part of the silicon, packet buffer or traffic manager tends to be a fixed function because it deals with the full cross-sectional bandwidth of the switch. So if 70% of the silicon area ordained to be the fixed function, then only 30% needed significant attention. And our hypothesis was that if we redesign this forwarding pipeline in a very specific way and meet these budgets, we should be able to produce something comparable to our fixed function counterpart. And in this process, even if it tends to be a bit wrong, we should still be within 20 to 25% of overall increase in chip area or power. And this is exactly what we set out to do to validate our hypothesis. So we took the traditional feed-forward pipeline structure of the fixed function devices and made every element programmable. What we needed to do was the programmable parser to take the packet header fields into the registers. Bunch of match action units identical for header transformation using VLIW instructions, ALUs, SRAMs and TCAMs for table spaces, counters, meters, and etc. And at the very end, you need a deep parser to put everything back together with any header anywhere paradigm. Similarly, the egress pipeline is made identical. And in this way, a new pizza architecture was born. Now, users can write their forwarding logic in a domain-specific P4 language, which compiles down to these match action units. Here you go. Now you have a whole programmable switch. This all sounds very trivial, but trust me, it took us few good years to produce a silicon at 16 nanometer. And that was Intel Tofino 6.5 terabits per second switch, empowering the network community since December 2016. Now you might say this all looks good, but did Tofino actually deliver to its promise? I would say yes, but why should you take my word for it? So here is a comparison table side by side comparing two switches. Both are available from an esteemed OEM. As you can observe that Tofino turns out to be a bit better on multiple dimensions, not just one. This begs the question that was Tofino a fluke? Can this really be repeated? Or is there an evidence that switches can be programmable and meet speeds and feeds? Skepticism is valid. We may or may not know long-term answer to this question. However, I can tell you for sure that it appears to be true at 12.9 terabits and 7 nanometer. I am very pleased to introduce Intel Tofino 2, the second generation of our pizza instance. It is designed or built on the same base architecture as Tofino, but to fuel the innovation in data centers, we double down on the programmability. We provide more processing per packet, more efficiency, better quality of service, and even enhanced advanced applications. It packs 260 56 gig SerDes with 12.9 terabits per second of switching throughput, 6 billion packets per second of P4 programmable data plane, a large packet buffer, unified, fully flexible, with added flexibility and visibility supports. All of this as lower performance per watt than Tofino reiterates that the programmability is achievable within reasonable budget, within reasonable cost. And all of this was put together using the multi-die package. We took the advanced 2.5D packaging technology and packed all of this together. This allowed us the switching silicon to use the 7 nanometer as a leading process node while letting the Ethernet PHY to trail behind. We designed our own inter-die communication interface as bunch of wires. It's the wide parallel buses running at higher speeds. The switch die has 4 pipes each running at 3.2 terabits per second and supports in total 30 to 400 gig ports. Now let me walk you through some hardware level improvements we achieved along the way. In anticipation of many more advanced use cases to develop, we increased the number of match action stages per pipeline by 67%. And each of these stages were also improvised to provide more VLIW instructions, multiple instructions per table, enhanced stateful capabilities, hardware learning, stateful FIFOs, primitives, etc. The unified packet buffer took the heavy uplift. It handles 25 terabits per second of read and write bandwidth in aggregate from 4 pipes. It's like writing a 25,000 bit wide memory every clock at 1 gigahertz. Queuing system handles 6 billion packets per second of NQ and DQ operation and supports non-blocking behavior. Each of these 400 gig port provides 128 queues with hierarchical quality of service support. All of this seems to be a really hard problems, but we figured it out a way to do a fully unified, fully flexible, non-blocking packet buffer to provide the better burst absorption. And on top of all of this, the TM is exposing more of its internal state for forwarding pipelines to make better visibility and control decisions. For example, this animation shows how the queue occupancy state is being transferred to the ingress pipeline as and when queue occupancy state changes. Now you can see that ingress pipeline can make a decision based on the congestion of the port or the queue. It can choose to avoid a congested paths or make some other determinations. All of this is just change of few lines of P4 program. This second example shows the power of I/O modularity, whereby here the Intel Photonics team and Barefoot team collaborated together to produce the world's first 12.9 terabits per second co-op package optics solution. It was demonstrated in March this year and received rave reviews. Now I will hand over to my friend Chang, who can walk us with the advanced application use cases at network wide using all the good things Tofinos provide. Thank you.
Great. So now that Anurag gave an overview of Tofino and Tofino 2, you may be wondering how people are taking advantage of the programmability of Tofino series in real world. Of course, there are a few obvious but still very powerful use cases. For example, a lot of our customers are simply reducing their switch data plane design by removing unnecessary features and repurposing the hardware resources that are sort of squatting in the chip just to increase the size of the tables they care. And doing so in P4 is as simple as commenting out a few lines of P4 code in the program and then recompiling it. But today I wanted to talk about a couple other more impactful use cases, and the first one is all about data plane telemetry and real-time control of your network. So imagine that you're running a large-scale network, and then there are a bunch of servers and switches interconnecting between the servers, and then packets are going to be flowing within this network. What you really want to do as a network admin is actually picking any packet, right? Not just some special probe or measurement packets, but pick any packet and then ask this fundamental question: which path did you take? Right, so I'm looking for an answer like this one. Hey, I'm packet X and then I visited switch 1, 2, and 3 at this time. And the second question that you want to ask is which rules did you get matched at each switch, so that I can explain why you took that path rather than other path. So the answer that I'm looking for is something like this. Okay, and then the third question the admins may ask is this latency question. Hey packet, how long did you end up spending at each switch that you went through? And the answer I'm looking for is something like this. And then all of a sudden I realized that at a particular switch this packet has experienced a significantly large latency. And in a packet switching system, the only reason why such a large latency can happen is because of queuing. So you can actually plot a queuing latency real-time time series like this one. And the last question that you may ask is, okay, now that I see this sudden increase of queuing latency, why is this happening? And to understand that, you need to ask this last question. Hey packet, when you were in the queue, what kind of other packets did you see? So that I can actually attribute the problem to the tenants or applications who caused the problem, right? Now, so these four fundamental questions, you may be actually surprised to hear that in the networking community, they couldn't answer these questions up until now. And And this may sound so surprising because in computing and storage industries, of course, you can collect a lot of fine-grained and useful information like this one. But networking, this is the first time, and that's the beauty of programmability. So we can for sure now tell that, hey, the programmability on Tofino and Tofino 2 and some, large data processing system like Deep Insight that we developed can allow network users and admins to answer these 4 fundamental questions. Okay. Now, let me talk about specifically how we do this. There are a few ways of doing this, but let me just explain a couple ways of doing this in our system design in P4. So the first idea is what we call INT, in-band network telemetry, and the key idea is very simple. It's all about having packets work as log packets for themselves. So what do I mean by that? A packet is arriving at a switch and then it's about to be forwarded out. But if you think about it, each switch actually has all the right information, like switch ID and arrival time and so on, right? So that information is actually now added to the packet itself. And then that's shown as this vertical small blob here, and then the purple one, and then the next switch actually adds its own metadata information, the yellow blob, and then the last stop switch does the same thing, and then finally when this packet arrives at the final destination, you can just collect only the metadata information and then send original packet back up to the receiver. So this mechanism is what we call INT, and it's so powerful. But if you think about it, you can instrument every single packet this way, but you don't want to generate report for every single packet. If you did, then you would eventually, increase the network workload just 100%. So you need an intelligent change detector, and what the change detector does is actually intelligent suppression of report generation. So the switches still, inspect every single packet, but it knows when to generate an important message. For example, when it sees the first packet of a flow or last packet, or when existing flows path or latency swings significantly. This is a very powerful mechanism and a lot of our customers are using it, but some customers are slightly worried that, hey, I'm changing the original packet, although I'm undoing all the changes at the last stop, but is there any way I can get the same benefits without touching original packets? And of course you can do that thanks to the programmability you have. So for example, the packets arrive at the first stop and then it can generate a separate report comprised only of the metadata, and then second switch does the same, last switch does the same. And then of course you can apply the same intelligent change detector mechanism at every hop. So this way you can actually collect metadata for every packet upon this sort of change detection. Okay. So this is a single slide, simple snapshot of the power, showing the power of INT. For example, when you have a congestion or microburst in your network, this is showing you how the congestion is actually broken down at the flow level. So at the center, you see the exact point that you're observing in a switch. And then, within plus minus 100 microsecond time window, you can see that some flows are arriving and leaving, and you can actually tell that which flow is most attributable to this particular micro congestion that you had. Another powerful way of using this INT is not just for monitoring, but to do your own congestion control. So for example, Alibaba and a few other prominent universities in US have come up with this new and powerful congestion control algorithm that actually improves the state of the art. And today in large data centers, TCP or variations of TCP or timely and DCQC and Rocky V2 congestion control are very popular, but this one works even better. And the reason this works better is because it has really precise congestion or decongestion information encoded in packets as metadata, and the sender can quickly react to that. So one of the signature benefit of this HPCC mechanism is that it actually does what is called MD, multiplicative increase and multiplicative decrease. All the existing congestion control protocols did additive increase because when the link bandwidth is made available, it doesn't know exactly how much additional bandwidth is available, so they had to increase the rate very cautiously and conservatively in an additive fashion. Now with INT, they know exactly how much is made available, so they can actually increase the rate very quickly and improve convergence rate. So for example, when you compare HPCC with other state-of-the-art congestion control mechanisms, you can see that it improves it lowers the latency and also flows completion time significantly. Now, the second part that I wanted to highlight is actually just beyond just networking. So as you can easily now confirm that when GPUs or GPGPUs were made available, it was used for mainly accelerating gaming and graphics. But now this machine is doing a lot of other things, especially machine learning based applications. We believe that we'll see the same kind of explosion of applications given the general purpose programmability and high I/O capability of these P4 programmable data plane machines. So we're starting with networking applications like telemetry and analytics and congestion control, but already people have started building more powerful appliance and gateway devices, I/O intensive devices, and then you'll see even more compute related applications. These are sort of I/O heavy compute applications, and then you'll finally see even other types of applications. So for example, one thing that some of our customers and Intel did together is this machine learning deep neural network training acceleration. As you can see, training is a really powerful application, but as the GPUs get faster, the total training time is reducing, but the amount of time that is spent for communication, which is the difference between these two, blue and orange bar, actually increases proportionally. And the reason is because GPUs got much faster, but the network didn't get that faster at all. So you're actually wasting a lot of time when you do DNN training just for better networking. Okay, and then we're trying to address this problem by using, for example, the Tofino-based switch as an aggregation server. So when you run DNN training, multiple workers need to share these weight updates or tensors, and then periodically they have to share the same weights and then rerun their different models, and then they have to keep doing this. And then and if you think about it, this is sort of compute intensive but very I/O intensive application, and then you need some amount of storage in the switch, and our switch has a decent amount of SRAM, albeit is smaller than DRAM, but you can actually use a streaming protocol to pull the data from one worker and to pull the same type of data from the other worker, and then share the result, the average back with the workers, and then reuse these memory slots for the next updates, and you can keep doing this, right? So this is what we call the switch-based aggregation solution, and it works remarkably well. And then when you do this one, switches and the NICs can share some responsibilities, and switches mainly performs integer vector additions and counting and compression for detecting losses. And the net result here, when you compare this result with state-of-the-art NCCL or nickel-based reduction solutions, across the board, this solution actually improves the DNN training sort of speed by up to about 300%. Okay, so this shows the power of programmability available in high-speed switching ASICs. Okay, so let me wrap up at this point. And we can happy to, so we'll be happy to take more questions from you.
So we can go for the Q&A section now. Hello? Okay. Okay, so let me thank you for the great introduction. Let's take a look at the questions. Okay, the first question I have is from Michael. Can Tofino be used for non-Ethernet fabric? Is there any intent to take this direction? Can it handle 400 gigabit per second or 800 gigabit per second links?
Anurag, could you take this one?
Yeah, sure, no problem. So definitely Tofino. Hello, can you hear me? Hello? I'm not sure we can hear you. Can others hear me?
Okay.
Hello?
Yeah, I can hear you.
Can we go ahead with the... Hello, can you hear me? Okay.
Okay, sure.
Yeah, okay, great
Yeah.
presentation. The first question I have is from Michael. Can Tofino be used for non-Ethernet fabrics? Is there any intent to take this direction? Can it handle 400 gigabit per second or 800 gigabit per second links?
Thank you for the question. Definitely Tofino designed with the Ethernet MAC on the die. So at this moment, it only talks the Ethernet protocol, but since the chip is fully programmable, it doesn't tie up to the standard full Ethernet L2 header. You can define your own L2 header as long as you pass through the basic MAC level checks. After that, the chip is completely agnostic to the type of the protocol. But today, Tofino 2 already supports 400 gig ports. So is the question about a single link 400 gig? That it's not there, but 400 gigabits per second is currently supported on Tofino 2. Okay, next question.
It seems Yuan is disconnected from this. Not
Yeah, looks like
Anurag. Yeah.
some technical difficulty.
We can see a few questions on the Slack channel, and we can probably answer some
Yes,
of
we
them.
can hear you. Yes.
So do you want to pick up the Slack channel? Chang, why don't you pick one of the telemetry questions by Sarah Biabani?
So yeah, Sarah asked whether time source synchronization
Yes,
is critical or not. It depends, right? Especially in data center environment, if you can collect in to out latency from each and every hub, you don't need to synchronize all the switches because every switch will generate its own arrival and departure time based on the same time source within that switch. And then if you sum those up, you get the entire end-to-end latency. And especially in data center, the link latency is also already known a priori because it's the link that you built, right? So some of all these things can give you a nice one-way or RTT latency. But if you're using this technology on where link propagation latencies can vary, yes, it may be useful to synchronize the time sources using something like PTP.
Yeah. Thanks, Sean. And there are a couple of questions on the collectives, essentially SwitchML.
Yeah, so How can we compare this with Mellanox Sharp? It's a similar technology. We don't know a lot of technical details of Sharp yet, so I can't make sort of quantitative comments in terms of throughput or latency. But in general, we're doing roughly the same thing. But the nice thing about Tofino is that it's implemented in P4, and you can actually modify it very easily if you want to customize it further.
There is a question recently came about and there are a couple of questions. One question was related to the die size of the core die, and then this next question is about the size of the TCAM arrays. Especially die size is definitely a proprietary information, confidential. We don't talk about those to outside. And for TCAM arrays, definitely this is same as every stage of the pipeline has the similar TCAMs as the Tofino devices we had. We have more of the stages in Tofino 2. I'm not certain how long we have for Q&A.
Yeah. Do we have more time for Q&A? We can barely hear you.
Okay. So, one more question, I think.
Yep, sorry to interrupt. We are going to switch onto the second talk of this session, which is from Pensando about their distributed services architecture. Our speaker is Francis Matus. He is VP of Engineering at Pensando Systems, had a 15-year career at Cisco before that, and has built over 20 production chips in the CPU area. So please go ahead with that.
Okay, thank you. Good morning, good afternoon, or good evening. Being a virtual conference in the COVID time, it's hard to tell where people are, but I'm guessing that we have people across the globe and for sure across the time zones. So my name is Francis Matus, and I'm the VP of Engineering for Pensando Systems, and I'm pleased to present to you today the hard work of so many people in our company across systems, hardware, software, and chip design. The title of my talk is Distributed Systems Architecture, or DSA, and we'll focus on the chip architecture at the heart of our DSA services. But before we get into that, I'd like to first give an overview of our system architecture, keeping in mind the problems and use cases that drove our solution. We were solving several problems associated with the management, scale, acceleration, and topology of services in today's data center networks. Besides moving the infra workloads from the host CPU cores to the IO peripherals, we were also providing a unified and consistent approach for defining, applying, and monitoring policy to bare metal, virtual machines, or containers. While we're also trying to provide all of this at significant scale at very high speed. So whether you're a cloud provider who wants to free up server CPU cycles and some DRAM and monetize those vCPUs, or you're an enterprise that would like a similar unified approach to managing heterogeneous workloads, or you're a service provider that wants to accelerate scale services like IoT on a 5G radio network, the Pensando Distributed Services Architecture solution reduces the complexity of the network topology, reduces latency and jitter, avoids bottlenecks and network switching central appliances, reduces the overall cost of these services while increasing the scale and bandwidth. The way we do this is we centrally manage networking, security, and storage services, which are implemented at the server edge and what we call the Distributed Services Card, or DSC. The DSC is a PCIe or OCP 3.0 form factor card, and at the heart of it is the Pensando chip, the remaining subject of this talk. At a high level, the Pensando chip architecture can be divided into two main paths or functions. The first is a networking function responsible for managing the Ethernet traffic to and from the network, a software-defined data plane for processing packets at very high rates, and a flexible DMA engine for high-speed transfer of data into and out of work queues. These are the underlying producer-consumer models for software-hardware interaction. In fact, in the last talk, you saw the basic blueprint of what a P4 processor would look like. Pensando believes that the P4 language is best suited to describe these tasks. It is a domain-specific language based on a match action construct, offering the benefit of programmable pipeline cores running at hardwired rates. This is the area where Pensando has provided most of the chip innovation and has enhanced P4 in some key areas. First, we've introduced a run to completion action sequence. So this allows us to trade off flexibility and resource management versus number of instructions per stage and performance. We've extended tables to large off-chip DRAMs, and this allows us to scale to millions of entries with hundreds of tables. We've generalized stateful updates into tables. So this gives us the ability to accelerate protocols in the P4 to run the protocols in the P4, like, for example, RDMA, TCP stack. We have a TCP stack running in the P4, NVMe, things of that nature. And lastly, because we are at the edge and we're PCIe attached, we've added the ability to exit a P4 pipeline with DMA transfers, whose command sequences are determined by the P4 program itself. So this gives us a very powerful way to stitch services together and to take packets coming off the network, operate them in the P4, and then operate them again in P4, sending them to the computer. The second path is an SoC function, which provides storage and security hardware accelerators, off-chip DRAM interfaces, ARM CPU cores for management, configuration, and what we call slow path or exception processing, PCIe functionality for providing services to the host, and a high-speed coherent network on chip that connects these different components to the P4 processors. Basic flows through the chip are network to network, giving us a bump in the wire type function, PCIe to network and network to PCIe, giving a standard Ethernet NetDev interface to an operating system, and PCIe to PCIe, which gives it like a hypervisor vSwitch offload function, if you will. Within the context of the blue box, let's take a closer look at the P4 pipeline. The pipeline starts when unsolicited packets arrive on the wires and flow through a programmable packet parser unit. Its job is to extract the described headers, take those fields from the packets, and initialize a data structure called a PHV with these values from the packet. This PHV will be the context. It'll hold a context for the packet as it traverses the 8 pipeline stages of the match processing units. I like to think of this PHV as kind of like the stack associated with the P4 program when it launches. Besides the 8 stages of match action, each pipeline has local SRAM, TCAM, and DRAM accesses to support P4 table lookups during the match phase. Once the packet has traversed all the stages of the pipeline, it exits into either a deparser unit, which uses the PHV to determine how to rewrite, remove, insert packet headers, or to a DMA unit, which uses the PHV, again, to determine the sequence of DMA commands to move headers and data to and from DRAM and update any hardware queue states associated with those work queues. Pensando is actively working with the p4.org architecture workgroup to help define the programmable NIC architecture and include this programmable DMA mechanism going forward. Each stage in the pipeline has 3 main units: the table engine, we call it the TE, the match processing unit, called the MPU, and the stage data path. The table engine is responsible for extracting fields from the PHV, applying P4 control statements, forming keys and hash addresses for table reads, launching those reads, getting the results back, and determining table hit miss status. The TE supports hash tables, TCAMs, or direct index table types. A single stage supports multiple independent table lookups per packet, multiple packets outstanding at the same time, and handles all pending table reads so that we can tolerate DRAM latency and maintain high throughput. We also have a locked table construct that handles dependencies between packets of the same flow. So a classic example would be a counter. The hardware handles stalling the issue of the next MPU program associated with the next packet until the dependency is resolved and forwarded. This is very analogous to a store to load forwarding operation in a processor. I like to think of this TE as the address generation and load unit of the P4 processor. The tables engine supports up to 2,000 bit wide keys and handles up to 3 layers of that will allow for up to 3 layers of encapsulated headers. Once the read returns, the table engine picks the next free MPU to execute the action statements associated with that table entry. The MPU starts its program execution from a program counter specified by the table and has 3 main data structures as input: the table key itself, the result of the table lookup, and the PHV data. During the execution of the action phase, an MPU can write back to the PHV or table entries in memory. This is the stateful notion of what we've added to P4. The stage data is a logical FIFO that keeps the packets in order as they graduate from one stage to the other, and is the local storage that holds a PHV, which can be up to 1 kilobyte per packet. Now let's look at the match processing unit in a little bit more detail. So the MPU, it kind of looks and smells like a standard CPU from an ISA perspective, with the exception of having some domain-specific instructions for protocol and hardware queue state manipulation. For example, when you process TCP sequence numbers, we have a special instruction that knows this is a 24-bit TCP sequence number, knows its location in the header, updates the 24-bit field, and handles all of the wraparound and the circular math associated with the 24-bit add. So this one instruction replaces a sequence of at least 3. The ISA contains also standard arithmetic, logical, data movement, and control instruction types. And we have 16 general purpose registers for local variable use when executing an action statement for a table. Here I show an example of an MPU assembly code sequence in a L4 load balancer. As you can see, the first instruction sets a predicate or a condition flag, and the following 2 instructions then do something based on that condition. So in our architecture, we tend to use a lot of predicated execution because the basic blocks tend to be small, and this avoids any kind of branch mispredict penalty, giving us consistent behavior in terms of jitter. The final component of the networking section is the packet buffer. Again, the packet buffer looks and feels just like a packet buffer you would find in a modern top-of-the-rack output queued Ethernet switch. The buffer is designed to tolerate startup latencies of the P4 pipeline. So when packets arrive and we start threads waiting for the initial results to start, handling Ethernet flow control, known as pause or PFC if it's per class, handle Ethernet costs, class of service scheduling, and also handles typical multicast replication, mirroring, span, things of these nature. Anywhere where we're multiplying the bandwidth, that's done in the switch as well. And we also provide a mechanism to extend our buffer into DRAM on a per cost basis. So this is if we needed to extend our buffer for different types of applications. If we came across something where we wanted really deep buffering, there are some applications in the 5G CMTS areas where we need some deep buffering, and so this comes in handy as well. Okay, so the next area of Pensando innovation comes around the PCIe interface. This interface is key because it exposes to the host all the services provided by the chip. And given that the services in the chip are programmable, this naturally leads to the fact that we need some level of programmability in the PCIe configuration space. Our PCIe device and functions can be set up by software at time 0, if you will. And we can expose different types of devices as configuration options during our initialization. So examples of devices that we can expose to the host would be things like a standard Ethernet controller, a Pensando Ethernet controller, an RDMA device, an NVMe drive, a storage offload or a security offload accelerator. We've even done VirtIO devices. So with a VirtIO driver, you can access our device. So this is a lot of work that's gone into here to enforce security across these PCIe functions and guarantee that host software that has access, device drivers, or even if they're user space mmap devices, can't access certain areas of the chip. So we made sure that the resources that are exposed in those bars are only exposed to that particular resource or that particular process. In addition to the software-defined PCIe services, ports can also be bifurcated into root complex and endpoints, and those can be going on simultaneously. And this allows for applications like if we wanted to do, say, intelligent thin provisioning on a host, we could have NVMe drives hanging off our PCIe bus and sort of be the man in the middle, or a bump on the wire, if you will, terminating NVMe and then initiating. Another application might be you have a sidecar where you have some sort of accelerator you have some new algorithm that you want to accelerate in hardware in FPGA, or you have some kind of coprocessor offload for which we will orchestrate and be the root complex for as part of the natural data flow. So we put a lot of effort into what's called PCIe multi-host support. This is where we want to be able to have resource management within a device per queue, or let's say we've taken the resources and divided them up logically across different PCIe ports, which each represent hosts. And we put a lot of work in to make sure that one host can't affect the other. If one PCIe resets, the other PCIe ports keep going. If one host is stalled on the receive, the other hosts continue to receive packets. And we find that this could be a very useful way to amortize 100 gig and even 200 gig connectivity to the TOR across multiple CPUs. So zooming in on the green box, which is the SoC block that or the path we had talked about earlier, we have a high-speed AXI compliant network on chip, a NOC, which is an interconnect that kind of forms the backbone of this embedded general purpose computer we have in this SoC part. It connects the CPU subsystem to the DRAM controllers, IO peripherals like UART, SPIs, eMMCs, PICs, interrupt controllers, things of that nature. As well as our hardware acceleration engines. The CPU subsystem is comprised of ARM A72 quads connected together with dedicated coherent interconnect, and we boot SMP Linux, Yocto. The interface between the P4 data paths and the CPU programs is provided via a classic Linux NetDev device or through DPDK. We support a doorbell is a mechanism for software to notify hardware that there is work to do in a queue. And so we provide doorbells for up to 16 million hardware queues. And these hardware queues can be divided across different types of applications. So for example, RDMA can have some of those hardware queues. TCP could have some of those queues. Your classic Ethernet could have some of those queues, things of that nature. And associated with these 16 million queues is a multi-tiered or hierarchical scheduler that allows us to provide scheduling services for what's considered solicited traffic by the chip. So when the software rings a doorbell, that we consider solicited traffic, because now the chip gets to decide which doorbell when there's multiple outstanding. And so that's a big part of how we can guarantee, for example, we can reduce the noisy neighbor problem between VFs in a virtual environment, or we can give storage and Ethernet different classes of QoS. And then lastly, in this block, these or let's say these interfaces, these networking interfaces, is a way for the local arms to provide services to management. So you may be running on the arm some type of control plane or some type of agent for interfacing to a controller. And so the ARM needs to be able to access the network as well. And again, that is done through standard Ethernet or through DPDK drivers. Besides that, we run standard DPDK and Ethernet drivers for a whole host of operating systems, different versions of Linux. We have one for BSD, ESXi, and Windows. And this provides standard networking services to the host. They see this device as just an Ethernet device, and then we do our work after that. Turning to the security services, we have security ingrained in all aspects of the chip, and it starts at time 0 with a built-in secure boot process. We have a small embedded security processor that reads immutable code from an on-chip ROM and works in concert with a physically unclonable function. It's called puff, and we use that to derive a device-specific key that never leaves the chip. Puff is a mechanism that uses on-chip SRAM to derive a unique signature for that chip, and from that signature, it is used to generate attestation keys, storage root keys, private-public key pairs, things of that nature. The secure boot process guarantees that only signed operating system images can boot on the device. The security services include asymmetric ciphers needed to accelerate certificate signing and verifying, to generate public-private key pairs, and all of these mechanisms are used in TLS or in OpenSSL when connections are established. In addition to that, we also have symmetric ciphers, which are used in the data path, and that is typically done for encryption for data in motion or for data at rest, but it's usually done on blocks or packets. These hardware accelerator units are available to software running on the host or on the ARM CPUs or to software running on the P4. Last but not least are the storage accelerators. We provide a rich set of data-intensive storage functionality with the ability to chain these services in a programmable order. The order of chained operations is specified by the offload driver APIs, but orchestrated by the P4 software so that we can do this at rate. So we can stitch the service as we go. We can first compress, and then we can put a CRC on it, and then we can encrypt it or in whatever order is specified that makes sense. We provide block compression and decompression. We provide erasure coding for RAID. We provide data integrity for protecting data while in flight, and deduplication hashes for data compaction. Similar to the security offload engines, the storage accelerators are available to software running on the host, ARM, or on the P4 pipelines. So for software developers to be able to take full advantage of the programmable nature of the hardware pipelines, we have developed the P4 compiler toolchain. The compiler is based on the open source front end available from p4.org, but has a Pensando developed custom backend, which is partly based on LLVM. The compiler takes in P416 source code and generates all of the configuration for laying out the tables, defining the keys, defining the structures, performing the programming for the parser graphs, and generating the MPU code for actions in the routines specified by P4. Currently, the compiler is within 85% of the performance of optimal handwritten assembly code, which we feel is a good trade-off between productivity, maintainability, and performance. The compiler has helped our software teams target the same code from one chip to another. As I'm sure everyone is aware, the compiler is always an improving work in progress, and we continue to work on optimizations. So here are block diagrams of the two chips we have built at Pensando since We founded the company in 2017. The first chip, codenamed Capri on the left, was built in TSMC 16 nanometer and is currently shipping. The second chip, codenamed Alba, is built also in TSMC, but in 7 nanometer, and is up and running in the lab. What I would like you to take away from the slide is the architectural consistency between the two designs. Alba is backwards compatible with Capri software, and besides exploiting process technology, it brings more of everything. So the biggest changes are around scaling the compute bandwidth of both the P4 and ARM processors, as well as drastically increasing the memory capacity. The chart on the right kind of shows the key differences between the two chips in their implementation. So for example, we added PAM4 SerDes for next generation top of rack switch connectivity to the server and to support 200 gig Ethernet. We added 400 gig of PCIe bandwidth, optimizing for 200 gig to the server and 200 gig to a root complex for NVMe drives or offloads. We increased the memory capacity from 8 gig to 64 gig so that we could provide more memory to the ARM for computing and continue to scale the size of P4 tables. We quadrupled the number of ARM cores based on customer feedback, specifically for being able to lift and shift storage stacks running on the hypervisor and for running more control agents. We almost doubled the P4 processing frequency while adding more P4 pipeline stages. We increased significantly the size of the last level cache to compensate for the DDR4-5 change from HBM. And we did lots of internal microarchitectural optimizations to avoid using memory in the first place and bouncing off internal SRAM buffers. Lastly, we added multiple nodes for optimizing power, multiple modes for optimizing power by closing timing across different frequencies and voltages. And finally, on the left is some performance data on an example networking service. So in this SDN bump in the wire application, we provide routing, we provide the overlay underlay function of NCAP decap. I believe we were doing 3 layers in this example. Stateless ACLs, stateful L4 firewall, where we're doing connection tracking and maintaining the reflexive ACL nature, and policers and QoS, as well as statistics functions. So the ARM, this is not a single flow table lookup and I'm done. This is all of these functions happening, and they're happening together. It's a pipeline. So you do routing, you do ACLs, you do all of these things. So the ARM processors work in this example in concert with the P4 pipelines to handle the connection setup for the first packet of the flow, because we are doing a stateful L4 firewall. And this is what determines that connections per second metric. But then the P4 pipelines take over and process all the remaining packets. And you can see that on Capri, we can get 40 million. And on Alba, we're doing about 80 million. And the other thing I'd like you to take away from this is the jitter, being in the single digit nanosecond range. So this is clearly providing hardware-like performance, but with this P4 programmable flexibility. We believe P4 is the right language to be doing computing at the edge for these types of workloads. And we've proven this across 2 generations. So with that concludes my presentation. Thank you.
Great presentation. Can you hear me well?
Yes, thank you.
Yeah, so I think that we are running out of time, but there's one question that many audience ask. I would like to get the answer from you, is that why you switch from HBM to DDR4-5 in your 7 nanometer technology?
Great question. So the main reason for switching to DDR comes for memory capacity. So HBM, as you know, are fixed capacity chips, and the only way to increase the capacity is to add more beachfront or to add more interfaces and to add more chips via modifying your silicon. So unlike DRAM, which gives you the flexibility to through DIMMs to have 8 gig, 16 gig, 32 gig, 64 gig versions on 2 channels, HBM forces that up front in the decision when building the ASIC. And so that's the main reason. The second reason is that after going through a second generation of this chip and really got to understand the fundamental data paths, it became, we realized that it wasn't necessary to be bouncing everything in and out of memory, that normally you just need a buffer to be able to handle the transit time or the latency through processing units. And so we started to use SRAM a lot more intelligently in the second design. And the last reason is it obviously reduces the cost.
Reduce the cost, okay. Thank you. Maybe one more question. If
Sure.
update the P4 policy or software, will root of trust be re-verified for CIA?
It depends. So for FIPS certification and compliancy, where you define the boundary is important, and that software can't be modified. But every time we, but we can continue to modify other pieces of the software infrastructure without having to go recertify. With respect to having to resign the images, yes, every time you would create a new image or change your binary, you would want to recertify that. That would be the best security policy. Although you don't necessarily have to do it that way, but that's what we would expect, is that you would update the image. It could be done dynamically, but probably not the best security process.
Okay, great. I see that your colleague Mike has answered many questions at the Slack channel. And due to the time limitation, we will move on to the next talk. But I will encourage you and Mike continue to answer those questions at the Slack channel. Thank you. Yeah.
Absolutely. Thank you.
Yeah. Yeah. Okay. Yeah, let's move on to the next one. Okay, so the third presentation is from Fungible. Our speaker, Pradeep, is the co-founder and CEO of the Fungible. And his career, including founding the Juniper network, the company widely recognized for inventing and industrializing the silicon-based router, the invention that played a central role in bringing about the internet age. Over the years, he has held several key roles in Juniper, including as the founding CEO and chairman, then vice chairman and CTO, and now chief scientist. Pradeep had a hand in the inception, design, and development of virtually every product Juniper shipped from 1996 through 2015. Before founding Juniper, Pradeep worked at the computer science lab at Xerox PARC for 11 years, developing design tools and microprocessor architecture. During this period, he invented the first cache coherence algorithm for package switch buses and made fundamental contributions to some microsystems, high-performance microprocessor servers. He holds a bachelor degree in electrical engineering from the IIT, as well as a master in electrical engineering from the University of Hawaii. In addition, Pradeep holds both a master and a doctorate degree from computer science from CMU. He is a member of National Academy of Engineering and holds more than 200 patents. Let's welcome Pradeep.
Good morning. I am Pradeep Sindhu, co-founder and CEO of Fungible. Today, I'm excited to tell you about a new technology breakthrough called the Fungible DPU. The DPU sits at the intersection of network, compute, and storage inside data centers. But first, I'd like to say a few words about Fungible. Our mission is to revolutionize the performance, economics, reliability, and security of scale-out data centers. The core technology that we're going to use to accomplish this is called the Fungible DPU, a new category of microprocessor and its associated software. Since this is a chip conference, I would like to take pains to emphasize that we're not only building chips and low-level software, but we're using this core technology to build systems and solutions to improve data centers. Please stay tuned for news on these systems. It is important for me to set the context for the invention of the DPU, because we may not share the same assumptions about what problems are important in data centers. Here is a summary of the key problems we believe are facing scale-out data centers. First is that their footprint in terms of power and space is way too large. And this is because of two problems that we will go into detail in a few slides. These data centers have trouble scaling to very small as well as very large deployments. Because of technology limitations, the complexity of managing these data centers is exploding. And finally, the security problem is still unsolved. In addition to these problems, data centers are also facing additional headwinds. First, the network and storage performance is increasing much faster than the performance of compute. Secondly, applications need access to ever larger data sets. Thirdly, Moore's law is slowing down and will eventually plateau. And finally, the security attacks are becoming increasingly frequent and more sophisticated. Now, the complexity of dealing with these headwinds threatens to undo the agility and economic benefits of scale-out. We believe data centricity will drive the next generation architecture. We call this architecture hyper-disaggregated. In this architecture, there are a small number of server types. For example, general purpose compute x86 servers, GPU servers, SSD servers, and hard drive servers. Each server is powered by a DPU, which connects to standard IP over Ethernet network. This fundamentals-based approach required us to confront the root causes of problems in data centers. There are two really important problems. The first one is inefficient data interchange between nodes. Second one is inefficient execution of data-centric computations inside nodes. A data-centric computation is a computation where all work arrives in the form of packets. These packets belong to many, many different contexts. The computation is stateful. And finally, I/O dominates arithmetic and logic. Examples of data-centric computations are the network stack, the storage stack, the virtualization stack, and the security stack. These are not the only examples, there are others as well. There are three other problems which are also important, but they're less important than the top two. And these are unreliability, inflexibility, and insecurity of the infrastructure. The Fungible DPU's design addresses all 5 root causes in a single device. And this is really important. First of all, it implements very efficient interchange of data between nodes in a data center. It performs data-centric computations at least an order of magnitude more efficiently than existing engines. It provides fundamental improvements to the reliability of network and storage. It supports strong end-to-end security. And finally, it is fully programmable. Now, you may be wondering where the Fungible DPU sits in a data center. Well, it sits inside each server. On one side, it connects to PCI Express, and on the other side, it connects to standard Ethernet. Inside the compute nodes, it complements CPUs and GPUs respectively. In storage nodes, it connects to SSDs and hard drives. Now, each server through the DPU connects directly to a standard IP over Ethernet network. And very significantly, the DPU implements the endpoint of what we call True Fabric. True Fabric is a network technology that provides some fundamental attributes that are needed. And these attributes include full cross-sectional bandwidth, low latency, low jitter, end-to-end congestion and error control, and strong security. The remainder of this talk focuses on the first of two DPUs we have built, the F1 DPU. The Fungible DPU consists of 8 data clusters, a control cluster, some memory and I/O interfaces, and a very fast on-chip network. The data clusters do the actual work of data path. They have 192 general purpose CPU threads, which are fully cache coherent. These threads are very tightly integrated with a set of carefully chosen accelerators. The control cluster itself is designed to run standard Linux. It has 8 processor threads, and it contains a secure complex. The memory and I/O interfaces on one side connect to PCI Express. On the other side, they connect to a standard Ethernet network. And the external memory is of 2 types: standard high-capacity memory, which is built using DDR4, and then high bandwidth memory, which is built using HBM. Now, diving into the data cluster itself, the data cluster, of course, runs the data path. It contains 6 cores, each core having 4 threads. These are simultaneous multi-threaded cores. There are also 6 accelerators. These accelerators are very tightly coupled to the general purpose CPUs, and they're also multi-threaded, heavily multi-threaded. And the accelerators are responsible for data movement, data lookup, data security, data reduction, data protection, and data analytics. Turning to the control cluster, the control cluster runs the control plane on the DPU. It has 4 cores, each which is 2-way simultaneous multi-threaded. Now, the control cluster has very, very strong primitives for security. These include a secure enclave, which is responsible for secure boot, for storing keys, private keys securely, so a secure key vault. It is also responsible for signing and authenticating binary files. So before any program can be run on the DPU, it has to be a signed binary. We can provide the same functions for attached applications processors like CPUs and GPUs. There is also a public key engine, which implements RSA and elliptic curve algorithms. There is a true random number generator, and there is also a physically unclonable function, which prevents theft of intellectual property. Turning to some more details on CPUs, caches, and external memory, the CPUs are MIPS64. It's a 9-stage, dual-issue, 4-way simultaneously multi-threaded pipeline. This pipeline also has a floating point and a SIMD unit. The IPC on data-centric workloads, along with switching threads every few hundred nanoseconds, is close to 1.5. These CPU cores support full hardware virtualization. They have large layer 1 and layer 2 caches. The layer 2 cache is shared, and there is full system-wide cache coherency. And each of these CPUs or CPU clusters is connected to both a high capacity and a high bandwidth memory. The network engine is a very fast 800 gigabits per second full duplex engine. It's also very flexible. This engine supports the endpoint of True Fabric. It is also fully programmable using a P4-like language. The host engine is also very high performance at 512 gigabits per second full duplex, and it's also very flexible. There are 16 independent dual mode controllers. Each controller can be an endpoint or a root complex. When it is an endpoint for an x86, ARM, or other CPU, it provides hardware virtualization with SIOV. And here it has 64 physical functions and 1,024 virtual functions. It supports very fine-grained QoS support all the way to the CPUs. It also provides full software flexibility where network functions, storage functions, and security functions can be fully virtualized. When a controller functions as a root complex, it provides a high-performance abstraction layer, which is able to do fully flexible data and control plane operations. And it connects to and abstracts devices like SSDs, GPUs, and FPGAs. One of the key innovations in the Fungible DPU is a novel model for programming data paths. Now, in this picture, you can see that there are many software data threads. These threads run on the MIP64 CPUs. And then there are also many accelerator threads. And these two different types of threads are connected by a very high performance any-to-any on-chip call continue fabric. Now these primitives implement an abstraction that we call a dynamic data flow graph. And this abstraction is absolutely the key to executing data-centric computations at very high speeds and with full flexibility. Now what we have measured is that this particular model is capable of providing between 10 and 20 times the performance of any other engine available today. So the Fungible DPU comes with a complete software stack. Starting with the DPU itself, at the bottom is FunOS, the FunOS nucleus, which provides basic functions like timers and memory management. On top of that are 5 separate data plane stacks: network storage, virtualization, security, and analytics. On the control plane side, we have Linux, which runs on top of a very thin hypervisor we call Funvisor. And you have agents that run on top of Linux. Moving on to the software that runs on the x86, which is attached to the DPU in some cases, we have drivers and agents running at low levels. And then on top of that, we have drivers which might be running inside virtual machines. Finally, there is a set of software which runs on general purpose CPUs. It's a centralized software called cluster services. And this cluster services allows us to manage and deploy large numbers of DPUs which are running inside storage servers and compute servers. So as you saw, the DPU provides multiple levels at which it can be programmed. There is, first of all, the software that runs in the DPU itself, the control plane as well as the data plane. Both of these are fully programmable. Then there is software that runs on an attached x86 or ARM host. You have the operating system drivers and agents that run on top. But we also can run data path code, which is defined on the x86, but it actually executes on the DPU via functionality like eBPF. And finally, there are the cluster services, which allows us to manage and deploy large numbers of servers that contain DPUs. Next, I want to provide you some performance data for the F1 DPU. Some of these numbers are measured, and some of these numbers are estimated. For TCP, we can do a single flow at 50 gigabit per second full duplex, and the aggregate, we can do 250 gigabits per second termination for TCP. For TLS, The session rate is 32,000 sessions per second. Stateful firewall at 370 gigabits per second. The OVS functionality at 400 gigabits per second. A load balancer at 256 gigabits per second. Block store read at 8 million blocks per second. These are 4K blocks. Video streaming at 256 gigabits per second, and selected elements of the TPC-H benchmark at anywhere between 3 to 100 times faster than these benchmarks run on x86. This slide shows the performance of True Fabric. We've actually selected 3 separate configurations where we want to demonstrate the latency under full load. In all 3 cases, we have 1,024 nodes. On the left-hand side case, it's the most innocuous case where each node is talking to a different node. In the middle case, you have each node randomly picking a node and sending a packet. And finally, the last configuration is where 1,023 nodes are talking to a single node. As you can see, in all 3 cases, the latency numbers themselves for all 3 configurations are in the 1 to 2 microsecond range. The utilization of the network is greater than 90%, and the ratio of the P99 latency to the mean latency is respectively 1.16, 1.57, and 1.02. These numbers are truly stunning. We believe we have invented a new category of microprocessor. You're all familiar with CPUs and GPUs. We'll now welcome the Fungible DPU. The architecture of this Fungible DPU is multi-core MIMD with tightly coupled accelerators. It provides very high throughput for multiplexed workloads. These workloads do not run efficiently on either CPUs or GPUs, fundamentally. The Fungible DPU implements True Fabric, which by itself advances the state of the art in networking. And overall, the DPU can perform data-centric computations somewhere between 10 times and 20 times more efficiently than CPUs or GPUs. We believe it is truly the third socket after CPUs and GPUs, and it will carry data centers for the next decade. So finally, in conclusion, we talked a lot about the F1 DPU, which is designed to sit inside a storage target, can also sit inside an AI compute server, or a security appliance, or an analytics appliance. Today, I'm very happy to announce our second DPU, the smaller S1 DPU, which is designed to go on a PCI Express card and to implement bare metal virtualization, storage initiation, NFV applications, and node security better than any other silicon which is available today. Both DPUs share the same architecture and the exact same programming model. Thank you for your time. I will now turn to questions.
Okay, great presentation. We have many questions on the Slack channel, and I see that Pradeep has answered some of them. But let me also pick some of the questions that are not answered yet. The first question is that, could you talk about why you use the MIPS rather than ARM or RISC-V? This is the first question, yeah.
Hi, Yuan. Happy to answer that question. This is a question we get asked quite frequently. We chose the MIPS architecture and a specific implementation of MIPS because it was the best one for solving the problem of executing data-centric computations very, very efficiently. And that was our highest priority. Now, that having been said, we do not depend strongly on any specific ISA. There's actually a great deal of misunderstanding in the industry on whether data-centric computations need a specific ISA. I think people generally understand that if I could only add a few magic instructions, that life would be much better. Well, I can tell you after having worked on this problem for maybe 5 years, and then at Juniper for similar problems for maybe 20 to 25 years, sadly, adding a few instructions does not help. This is a macro architectural problem. And so that's why we chose a MIPS. But our dependence on the specific instruction set of MIPS is actually very lightweight.
Okay, thank you. The second question is from Dan Wilkinson, and he asked, how would you compare the DPU to Pensando's Alba device in terms of technology and target markets?
So I would say that I can talk about the DPU and what markets it addresses and what specific problems it's trying to solve. I will let others speak for themselves. What the DPU was designed to do was to solve two critical problems in the data center. And I don't believe that there is any other company, startup or non-startup or large company, that actually has taken a clean sheet design approach to solving these two problems. And these two problems, as I mentioned in my talk, one of them is that node-to-node interactions between servers in a scale-out data center are very inefficient. That's problem number one. And problem number two is that data-centric computations, the way we define them, are executed very inefficiently on standard general-purpose CPUs. We have solved those two problems definitively and in a way in which they are programmable. And so that having been said, we will enable in scale-out data centers at small, medium, and large scales full disaggregation of resources. Resources like general-purpose compute, AI servers, and high-performance storage servers, as well as high-capacity storage servers. I don't believe that any of the startups, including Pensando, even pretend to solve that problem. Okay?
Okay, thank you. So one more question from Paul, and what he asks is, how does True Fabric different from standard Ethernet?
Thank you for that question. The answer to this question will require a little bit of explanation. True Fabric is not different than Ethernet. It is built on top of Ethernet. In fact, it is built on top of IP on top of Ethernet. So True Fabric is built on, it's a fully open standards technology, and as such, it interoperates with not only IP Ethernet, but TCP IP over Ethernet. True Fabric is best understood as a child of TCP. TCP was invented, some 45, 47 years ago to solve the problem of any-to-any communications in the wide area. If you look at the data center, the timescales are probably a few thousand times shorter than in the wide area. And it should be surprising to people that TCP has worked as well as it has. Well, the fact is that today, with the speeds of individual servers going to 100, 200, and eventually 400 gigabits per second, that software implementations of TCP are not going to cut it anymore. And so what True Fabric does is it takes the spirit of TCP and implements that in hardware on top of open standards. So hopefully that helps answer your question.
Okay, thank you. One more question. Would you be able to comment on how the architecture would scale beyond 400 gig line rate processing? Yeah.
Absolutely. So one of the most important things we did, Yuan, as you know, problems of networking are inherently problems at scale. And when you talk about scale, there are two different dimensions that it's really important to point out. One is the bandwidth of individual interfaces, And then the other is the overall capacity of a network. I think one of the mistakes that, again, the industry has made is to run after higher and higher speed individual interfaces. This doesn't help solve the fabric problem inside data centers. It actually hurts it. And it hurts it because I'm not talking about the overall capacity of interfaces coming out of a server. That we're happy to support. Actually, we do support currently 800 gigabits per second full duplex to a single server with a single DPU. And we can easily see our way going to 1.2, maybe even 2 terabits per second aggregate capacity. What I'm saying is that this aggregate capacity needs to be presented in the form of N by 100 interfaces, not as a single channel consisting of 800 gig, 400 gig, because that is essentially shooting yourself in the foot. And people who actually understand the networking problem do get this. Because running after higher and higher speed interfaces does one thing which is really bad. It actually reduces the degree of connectivity of individual switches. And when you reduce the degree of a switch to implement a certain capacity, you have to put more tiers of switching, which causes congestion and it causes high latency. And then people complain about those things. Well, that's a self-inflicted problem. Okay?
Okay, thank you very much. Due to the time limitation, we will move on to the next speaker. And there are many more questions on the Slack channel. So please go ahead and take a look at. Yeah, thank you.
Absolutely. I will answer as many of them as time permits. And they're very interesting questions. Yuan, thank you again for having me on.
Thank you. Thank you. Okay. Okay, let's move on to the last presentation in this channel, in this section. The presentation is from Alibaba, and we have two speakers. The first speaker, Dr. Zhang, he is a senior staff engineer in Alibaba Group. He's leading the heterogeneous cloud team in Ali Cloud. His research interests are on data center, parallel computing, GPU, and I/O virtualization. Recently, he has been working on the X-Dragon project. The second speaker, Dr. Justin Song, he's leading the system. He's the leading system architect and performance and power specialist in Alibaba Cloud. And he has been, prior joining Alibaba in 2016, he was with Intel for 14 years, working on server CPU cores, ARM core, and platform architecture. He received his PhD degree from Tsinghua University and holds more than 100 patents. Let's welcome Xiao and Justin.
Hello everyone, we are Zhang and Justin from Alibaba Cloud. Today our session will be two parts. First, I will introduce the X-Dragon, which is high-density multi-tenant bare metal server, and my colleague Justin Song will introduce the second part, the new technology of memory expansion and power management of X-Dragon. X-Dragon project in Alibaba Cloud was kicked off around 3 years ago, and the project now already on public, and if you are interested, you can check it out from our cloud anytime. If you have any questions, please kindly send us the email which shows on the front. Before we talk about the bare metal cloud, the first question is why we would like to develop X-Dragon. We also called it bare metal hive in our paper. X-Dragon bare metal cloud is actually a hardware-software hybrid system that enables the users to benefit from the native CPU and memory usages, and also the ability to access the cloud network and storage infrastructures from a software-defined virtual device. These virtual backend devices are emulated by bare metal hypervisor, which is our highly customized. The first reason we designed X-Dragon is for security and isolation. As we know, virtualization is sufficient, isolated, and secured by hypervisor in most of usage scenarios. However, such isolation is enforced mostly by software. They still share the same CPU and memory in system, This resource sharing gives a chance to malicious guests to attack the host and other VMs. For example, we know recently the side channel attacks. The best way to reduce this attacking service is using separate hardware for each guest. That is how bare metal cloud is created. While only bare metal servers are not enough, people want to have a low-cost service also. 70% of instances in our Alibaba cloud are small instances. The small means less CPU cores, less memory required. So the second design purpose is to support multi-tenant. The more guests we support in one bare metal server, the more cheap for our customers. X-Dragon to reduce cost by supporting multiple guests in single server with physical CPU and memory isolated for each guest. The third reason is for single thread performance. Nowadays in data center, we use big cores for all type of servers. These Intel Xeon processors tend to provide more cores in parallel, however lower base clock. So the i7 processors is much powerful than data center processors. With X-Dragon, we use separate computer boards in front end, which can adopt any type of processors other than base server. So Core i7, Core i5, E3, AMD, or even ARM processors can be used in the computer board. The last reason is manageability. The guests of X-Dragon instance could be connected into cloud infrastructures, thus share the benefits of elastic and manageability of existing cloud. Bare metal guests actually share the same images between KVM-based guests. From users' perspective, they are same instance except bare metal guest has native CPU and memory, while KVM-based guests are virtual one. We will look at the details in following pages. Nowadays, there are two major types of instances in data center and the public cloud, VM-based cloud and the legacy single-tenant bare metal cloud. Now we provide the third one, multi-tenant bare metal cloud. We compare the three types of cloud from density, performance, manageability, isolation, and also security in paper. VM-based cloud has better density than the other two. It can support as many as 100 guests in a single server, while X-Dragon can support up to 16 bare metal guests. It is already covering most of scenarios. While legacy bare metal server is only one person for one server. VM-based cloud has its drawbacks. It has non-ignorable virtualization overhead, limited single-thread performance, weak isolation because of sharing resource, and more worse with security concern due to side-channel vulnerability found recently. To this end, bare metal cloud has become an emerging type of service in the public cloud, where a cloud user can run dedicated physical servers. The bare metal cloud provides users with strong isolation, full and direct access to the hardware, and more predictable performance. However, the existing legacy single-tenant bare metal servers has poor scalability, very low cost efficiency, and weak manageability, because it can only lease entire physical servers to the user and have no control over to the user programs after the server is leased. Our solution combines the advantages of above two types of clouds. It has not only good density and elastic, flexible manageabilities, but also native performance and a strong hardware-level isolation and security. As the previous page already said, manageability is important. The design of X-Dragon will not to change anything of cloud infrastructure. They share same cloud VPC network, share same cloud remote storage system with KVM-based cloud, so the operators can use unified tools to maintain these two. In X-Dragon, each bare metal guest runs on its own computer board, which is a PCI extension board with dedicated CPU and memory models. By hosting up to 16 bare metal guests in single physical server, it can significantly improve the cost efficiency of bare metal service. From the left side diagram, you will see the architecture of KVM-based and X-Dragon-based cloud are very similar. On the SAN-based server, KVM-based cloud provides the multiple guests with its QEMU and KVM hypervisor, while X-Dragon supports 16 computer boards with our customized hardware-software hybrid system we call bare metal hypervisor. The both hypervisor provides I/O subsystem by emulated virtual backend in base server. The difference between two is VM guests share CPU and memory resource each other, while bare metal guest has its dedicated native CPU and physical memory. That is how bare metal hypervisor better than KVM based. Let's have a close look at how bare metal hypervisor emulates the I/O subsystem for bare metal guest. The left picture shows the overall system architecture of X-Dragon. Each bare metal server consists of a base and a number of computer boards. The base is essentially a simplified base server with a low-cost E5 CPU. Each computer board is a PCIe extension board to the base. Its main components include the CPU, memory, PCIe bus, and I/O band. I/O band is a piece of hardware implementation in FPGA. It interfaces with both PCIe buses on the base and the computer board. On the PCIe bus of the computer board, it emulates a number of virtual devices. From the guest perspective, each virtual device is a normal PCIe device that can be discovered, configured, and used. On the PCIe bus of the base, I/O band exposes the backend of the virtual devices and provides the interface for the hypervisor to control the execution of the computer board. I/O band acts as a bridge between the virtual front end of the guest and the backend in the hypervisor. Specifically, it forwards the control and configure commands by the front end to the backend and shuffles the data between them via a built-in DMA engine. Currently, I/O band supports the virtual devices for network and storage. Virtual devices are modeled as PCIe devices. A guest can discover, configure, and use virtual devices through its virtual PCIe bus. This allows the X-Dragon to implement a virtual in a hardware and software hybrid design. I/O band consists its front end and its back end models. The left picture shows the scheduling mechanism of I/O band, and the right side shows the back end working flow of I/O band. The front end of I/O band is attached to a PCIe bus of the computer board. The FPGA logic in I/O band emulates a PCIe interface for each virtual device. Access to this PCIe interface by the guest is directly forwarded to the backend for processing. In the virtualization system, the front and the back end exchange the data through a shared link buffer. However, this design does not work in our system because the front and the back end of the I/O band do not share the physical memory. Instead, they each have their own memory. To address that, I/O band creates a link buffer for both hypervisor and the guest. The link buffer with the hypervisor is synchronized to the other link buffer. When the data is added to one of the link buffer, it copied to the another one by the DMA engine automatically. The backend of the I/O band handles the received I/O request by packing and forwarding them to the corresponding cloud devices. The design of I/O band focus on how to connect our universal cloud infrastructure with how our performance. Similar to the KVM-based guest, in X-Dragon, all the I/O requests are handled in the user space with vhost user protocol interfacing to our cloud infrastructure, that is, customized DPDK vSwitch and the SPDK cloud storage. We used pull mode driver for both DPDK and SPDK. The pull mode driver pulls the virtual devices for I/O requests instead of relying on the interrupt. That can significantly improve the I/O performance by avoiding the interrupt latency. Now let's see our evaluation data and the real business cases, how X-Dragon performs better than those with the same configuration of the VM guest. The top two pictures shows the bare metal guest compared with the native and the VM guest. The CPU performance of three systems were close to each other. The overall performance of X-Dragon was about 4% faster than the physical machine, while the performance of VM was about 4% slower than the physical machine due to the overhead introduced by its resolution. For all the tests, the memory bandwidth of bare metal guest was almost identical to physical machines, both close to the speed limitation of 4-channel memory. However, the best performance of the VM guest will only reach about 98 of the bare metal guest under the load because of the memory resolution overhead. We also evaluated the network and the storage performance between bare metal guest and VM guest. The packet receive rate, we called it the PPS, was same for both types, but bare metal guest has more implied volatilities, and in application levels, they both have similar latencies with socket proof testing. For remote storage performance, we run FIO benchmark across the SSD backend cloud storage. Both the bare metal guest and the VM guest saturate the storage limitation, which is 25,000 IOPS. However, bare metal guest has lower average latencies, as shown in the picture. Specifically, the bare metal guest was about 25% faster than the VM guest in average, and 3 times faster in long tail latencies. A more important experiment is how well X-Dragon performs for common applications used in the cloud. To this end, we run latency, MariaDB, and Redis servers in bare metal guest and measured how fast they could respond to the query. For most of the popular applications, bare metal guest performed substantially better than virtualization-based cloud servers in the cloud.
Next, I will talk about two more features, memory pooling and power management of X-Dragon. Memory pool makes app development simple, enables easy deployment of large footprint instances, helps reduce memory cost. App-aware power management helps improve performance per watt and lowers cloud data center operation cost. As shown in this slide, we do memory pooling on the rack and also in the reach of high-speed data plane, which can be commercial off-the-shelf Ethernet switches or emerging dedicated switch fabric. In the rack pool, CPUs will be connected to a memory extension, so-called Memory X module, where cache coherent links all be connected to XNIC on generic PCIe links. Memory X can be shared among several compute nodes and can convert high-density on-rack memory, P-memory, or SSD pool into local memory for each compute node. Memory X can also work with remote pool to enable larger capacity and a more flexible memory configuration for compute nodes. Memory X sits on cache coherent links, but it doesn't have to use cache coherent protocol. Whenever and wherever non-coherent mode is more friendly to compute nodes, capacity or performance-wise, Memory X will serve bytes or pages to compute nodes. The XNIC simply establishes linkage between compute nodes and remote pool, with assumption that unavoidable long latency and low bandwidth doesn't hurt end-to-end application performance or at an acceptable level. On the remote pool side, CPU and/or dedicated hardware logic does as much near pool pre-compute and prediction as it can, and responds to remote memory X or XNIC requests. We did a preliminary ROI analysis. Memory pool can eliminate fragments and enable flexible CPU to memory ratio. it can use tiered memory media and lower memory cost by placing hot data in local DDR or unpackaged HBM, and moving warm data to rack pool and cold data to remote pool. Operation-wise, it enables easier and quicker migration, especially for large footprint instances. The near-pool warm-up hopefully improve performance scalability. In data center TCO analysis, we found it can help reduce number of server skills and enable denser deployment. It also has many other merits to enable new usage models and support smart control plane extension. Here is a closer look of the design on the compute node and the rack. We depend on ecosystem to make hardware faster, and we focus on software-hardware co-design, denoted by the green color. Our system software is responsible for memory allocation and page fault handling, as well as performance monitoring and optimization on the fly. In MemoryX, if cache coherence protocol doesn't support far reach of remote pool or doesn't meet applications' needs, we'll shift gear to use Memory Page Manager. It features memory page lookup and ordering management, poolside warm-up, prediction and prefetch, and some hardware acceleration. In its backend, we take advantage of mature NVMe over Fabric or other reliable transfer protocols for fast and reliable data movement. In this table is our estimated benefits. We addressed many scenarios, including traditional computes, middleware, microservices, AI, encryption and compression, instance placement and migration, checkpointing and mirroring, NFV, database, graph computing, upgrade and deployment. For small footprint instances and for instances with too short lifespan, there is negative performance impact when compared with 100% native DDR solution. But in other scenarios, we expect to see positive payback. Next topic is power management. Here is a global deployment scheme in Alibaba Cloud. We have a central decision-making mechanism called Resource Manager, also a bunch of region managers or AZ managers. And in each cluster of compute nodes, we have a power agent in each compute node, working in collaboration with aforementioned managers and also with SuperApp's local app agent. The power agent is responsible for power-related telemetry collection and power and performance control. Now, let's zoom into each X-Dragon compute node. The power and performance agent uses both in-band and out-of-band channels to monitor health and working efficiency of components such as CPU, GPU, DDR, storage, network, cooling fans, and so on. It also uses both channels to do the control. To be noted, the reason why we need out-of-band channel is largely because bare metal users probably are not ready to run our binaries in their OS. Even in legacy virtualized environment, we also want to minimize in-band monitoring and control overhead. Here are two examples. On the left-hand side, we use power management to do power limiting to avoid power outage. This helps increase data center deployment density. On the right-hand side, we do app-aware and fine granularity per core power budgeting and performance control for high-priority cores. You can see, as we lower CPU power budget, the high-priority cores can still run at a high frequency, but the low-priority cores might start suffering from performance impact. We have mentioned performance many times. Yes, performance is king. Any power management without performance awareness is incomplete and cannot be practically used. On the left-hand side is a contract between our power management platform and Elastic Compute Services. The contract includes many performance protection features. for example fmin. The lowest frequency during power capping must not be lower than previously negotiated value. This way we guarantee power capping doesn't disrupt cloud applications and services. On the right-hand side are two cases we captured in our data center that showcases how we meet requirements set in this contract. The top chart shows power capping triggered, but performance became unacceptable, so we stopped and used other methods to lower power. The bottom chart shows performance loss is okay, and we continue with power capping until we reach a safe power level.
Yeah, thank you for the presentation. We can move on to the Q&A section. So the first question I have is actually asking about why DPDK and SPDK running on host is not optimal for Alibaba Cloud. How do you solve the latency and bandwidth problems with memory pool? Okay. Yeah, we are trying to fix the audio problem. There's some technical issues. Oh, yeah, sure. Okay. So the question is why the DPDK and SPDK running on host is not optimal for Alibaba Cloud. How do you solve the latency and bandwidth problem with memory pool?
Hello, can you hear me now?
Yes.
Oh, you can hear me now, right? Sorry for this.
Yes.
Okay, sorry. Yeah, I just now answered part of the question. PDK and SPDK were very successful in forwarding traffic, data plane traffic, no matter it's storage or network. However, we noticed that on Alibaba Cloud, our customers do need microprocessor resource and try to use every compute resource and also how about right now? Okay. Yeah, and we realize it's very important to provide every compute resource to the customer to their applications. And also we need to minimize the overhead of the hypervisor running on the host. And in some cases, applications do need strong disaggregation and isolation. So they do not trust our supervised high priority DOM 0 running DPDK and SPDK on the host. So we do need to offload DPDK and SPDK to another component. In this case, we use X-Dragon to do all the acceleration. That's for the first question. And for the second question, which is the latency and bandwidth awareness when we do memory pooling. The latency for sure today, in today hardware ecosystem, even if for future PCIe Gen 5 we believe the latency cannot compete with the native DDR, native HBM. However, it doesn't mean we cannot use memory pooling. Instead, we focus on the software and application, and also the scheduling part for the instances. We try to maximize all the data performance, data opportunity, analysis opportunity by collecting all the underlayer, and also to work in collaboration with application owners and developers, and sometimes to take advantage of the service mesh. Then we can guess or we can get information from the users' heuristics that their applications or instances do not need that crazily low latency or high bandwidth, and some data is okay to be delayed. And they may also tell us the end-to-end performance. That's number one important. So the latency, it can be several hundred or nanoseconds longer than the native DDR mode. Uh, Using that way, we can take advantage of today's software scheduling and optimization opportunity. Then we can somehow use memory pool in a lot of scenarios. Although it's not perfect today, it's already started generating benefits to our customers, and also we do more exploration in the lab, try to give as low as possible cost and also as high as performance, especially the end-to-end performance. Okay.
All right, thank you. I have another question from Diva Bodas. He asked, is the power budget for each card allocated dynamically or statically?
And we do it in both ways. During the deployment campaign, we do pseudo static allocation. For example, we may install 20 or 21, 22 servers in a rack, and we calculate based on the online data what would be the per server and per rack power quota. That number can be a little bit static, and we use some AI theory to back support that calculation to make sure the power over budgeting possibility would be extremely low. Also, during the runtime, we use dynamic power allocation. When there is a surge in application, it's very hard to predict, and sometimes it can hurt performance if we do. In the presentation, we showed how we reach agreement with applications. Perhaps that's okay. And we can guarantee the minimum performance loss. And if there's still consistent and persistent power surge, then we have to use potential, for example, to use backup battery, or we start migration mechanism, and we can alleviate that problem always.
Okay, thank you. One more question. The microservers are isolated, but the memory pools are shared by servers and nodes. How could you avoid the security problem, say, for example, data leaking from the memory pool? Because one doesn't have to attack that server, but maybe through the memory pool, they can overlook other servers' work. Can you elaborate how do you make the data to be secure in this memory pool problem?
For the memory pooling, the encryption is a very important thing to consider. Also, it may mean a significant slowdown. And right now, we depend on the processor capability to encrypt important data. And also we depend on the link, the encryption, the decryption capability, and the link. Today in the POC phase, we only do static data allocation and memory pooling, and we guarantee for sensitive users their data will not be touched by other applications, other users. That means limited memory pooling in that scenario. Their data will never be touched and shared with other people. It of course limit the usage model and coverage. But we believe as a hardware technology and the bump in the layer of acceleration technology involved, we should be able to benefit from such hardware. And we should be able to provide all data encryption, decryption, and also authentication. All of that security features will be available. It's a work in progress. Before we are fully able to guarantee data security, we are going to limit the usage model and the coverage to make sure we have limited, but also already beneficial memory.
Okay. Okay, thank you. So we are running out of time, and there are many more questions at the Slack channel. So hopefully you and Xiantao can actually answer those questions at the Slack channel when you have time. All right, thank you very much for the great presentation.